So thank you so much, Ajit, for that very kind introduction. It's a pleasure to be here on this beautiful ICTS campus. This is my first time here, and I'm so delighted that the room is full of smiling students. The challenge I have for the students before I start is that you have to ask me some questions, okay? Today, before I dive into the talk, I wanted to show pictures of the graduate students and postdocs in my research group at Caltech. And I've been at Caltech now for 4 years, and by far the biggest perk of this job at Caltech, of being an assistant professor at Caltech, has been these amazing students and postdocs that I have both the pleasure and privilege of mentoring. So many of the results you'll see that I present today are thanks to these wonderful smiling faces, so keep them in mind. My connection to India and to the research that I'm doing is a project called GROWTH. So GROWTH stands for Global Relay of Observatories Watching Transients Happen. And what I study are cosmic fireworks. So I look for things that become 1 million to 1 billion times as bright as the sun, but then fade away in a few hours. So my biggest problem in life right now is quite literally sunrise. So I'm not even joking. You can laugh, by the way. This is an informal talk. So laughing is totally allowed, okay? And you can interrupt me anytime with questions. That's also totally fine. So what we do is when we make discoveries at Palomar Observatory in California, we discover fast fading transient. The problem is that we cannot gather all the information from it because the sun rises. And once the sun rises, you can no longer collect data in the optical and the infrared bands. Right? You need it to be dark to be able to see the stars, to be able to see the transients. So the way we solve this problem to study fast evolving transients, very young supernovae, fast moving asteroids in our own solar system, is by making friends around the world. So the subtitle here is a global network of observatories is how to make friends around the world. Because if you use jet lag or basically rotation of the Earth to your advantage, then once you discover a transient at, say, Palomar Observatory, you can continue to study it from Hawaii because the sun rises 3 hours later in Hawaii, right? And then after that, you could move to Japan, Taiwan, India, Israel, and Sweden, and continue to study the transient as the Earth rotates and always stay in the dark, right? And in this manner, you can beat sunrise. And in India, my partners, my co-investigators in India are Professor Anupama at the Indian Institute of Astrophysics and Professor Bhale Rao at IIT Bombay. And in India in particular, the GROWTH network actually built a new telescope at Hanle called the GROWTH India Telescope. And this has a fantastic half-square degree field of view on a 0.7 meter telescope. It's a fully robotic telescope dedicated to time domain astronomy. And GROWTH was founded in 2015. It's also 4 years old now, and there's a lot of fun that we're having. We're writing one paper every 10 days with this beautiful set of friends around the world. So the talk's focus today is on multi-messenger astrophysics. So let me explain what that is. When I say multi-messenger, I mean we are studying the physics of stellar physics from many different messengers. So we study using gravitational waves, using neutrinos, using ultra-high energy cosmic rays, and then data from across the electromagnetic spectrum. So we don't specialize in any particular piece of the electromagnetic spectrum because when we are trying to study these objects, the picture is incomplete unless you take data from the entire electromagnetic spectrum. So everything from gamma rays, X-rays, UV, optical, infrared, radio. We need to combine all these pieces of the jigsaw puzzle to try and understand stellar astrophysics. But in particular, there are a lot of facilities, a lot of excitement about this field worldwide. I'm not the only person. That I think 3,000 plus people working in this field right now. And one of the things that's sorely missing in this field is that there's no opportunity to do time domain astronomy in the infrared and the ultraviolet for very technological reasons. And I'm trying to overcome the infrared barrier right now on how do you open up the universe for exploration in the infrared wave bands. I'll touch upon that later in the talk as well. to about 1 micron. That's visible optical light, the light that our eyes can see. Now, beyond a micron is where infrared begins. So between 1 and about, I would say 5 micron is the near infrared. Between 5 micron to about 20 micron is the mid-infrared, and then beyond that is the far infrared, say from 20 to about 100 micron. But the infrared sky has been relatively pristine. The biggest camera, the widest camera that we have in our arsenal in the infrared is 0.6 square degrees. We as in the astronomical community. It's actually a European camera called DECAM on Vista, and it's only 0.6 square degrees. Now the moon is about half a degree on the sky, right? So this is not a very big field. In the optical, we are building 50 square degree cameras like this Wiki Transient facility that Professor Ajit mentioned in the beginning. So what is stopping us from building wide field infrared cameras? And the reasons are very, very simple. The first reason is that the detectors in the infrared are very expensive. You're beyond the silicon band gap, so you have to look to alternative semiconductors to be able to build detectors in the infrared. So it's just a question of cost. And the second problem that we have in the infrared is that the night sky is very bright. So when you're trying to study something in the infrared, you have to battle against this very bright background, right? It's all about signal to noise. And the background noise, because of the bright night sky that we have on planet Earth, is a bit challenging. So we're looking at ways of overcoming both of these challenges, and I'll go into that as well. So the way we are trying to solve this is that Rome was not built in a day, and you can't do anything by just waving a magic wand. So we are doing this in a phased approach, where we're doing multiple small experiments, baby steps, towards the bigger goal of opening up the infrared for the dynamic universe exploration. So we began with phase 1, which is just targeting nearby galaxies. If you don't have a wide field, why not just pick a few galaxies and study them? If you don't have an infrared camera, what if you can push to the red end of the optical? Then I'll talk a little bit about this Pathfinder project, Palomar Gattini-IR, and we've just started construction on phase 4 for the Winter and Dreams projects as well. And all of this is sort of leading towards the bigger dream, which is to go to the South Pole. Because on the South Pole, the night sky is darker than anywhere else on Earth by a factor of 40. So if you can gain that factor of 40 in a particular location in the electromagnetic spectrum at 2.35 micron, then that's where I really want to go. But you have to sort of do this in a phased approach so that you can make a credible case to go to the South Pole. And each of these, as you can see, are topics of PhD theses of my various students. So there's a lot of progress in each one thanks to the hard work of these PhD students. So let me try to put infrared transients in context for you. So as I mentioned to you, transients are cosmic fireworks, right? They are explosions in the sky that are short-lived. So how do you characterize them? If you were to pick only 2 parameters, how would you characterize them? The first one is luminosity. How bright is this intrinsically, right? So we know novae are about 1 million times the brightness of the sun. And supernovae up here are about 1 billion times the brightness of the sun. And this gap here is the 10 million, 100 million, which is just rare transients that are harder to find. And then you have some supernovae that even beat that billion and go even brighter because of interaction with the circumstellar medium. So that's the y-axis. That is how things are ordered on the y-axis. On the x-axis is time, right? I mean, the duration of the transient is what is setting the x-axis here. So when we did this very first step, the very first PhD thesis from my research group, which was looking with one of NASA's 4 great observatories, the Spritzer Space Telescope, we went and looked at 200 galaxies multiple times every year for the last 6 years. And we said, okay, what does the universe have to offer in the infrared? What stellar physics is quite literally hidden from our view because we haven't bothered to try and study the universe, the dynamic universe, the changing universe, in the infrared wave bands. So what that did from 2015 to 2019 is change this picture. So pay attention to this picture. This is as of 2015. And this is what it looks like now as of 2019. So you can see there's a whole bunch of yellow stars, purple stars, red stars. Each of this is a paper. Each of this is the topic of entire colloquia. So I'll just skim the surface and give you a little bit of information about each one. But I want you to focus actually on this light blue, these two light blue dots for the first part of the talk, which is labeled as a kilonova. So kilonova is something that's 1,000 times brighter than a nova, and it is the name given to the electromagnetic counterparts to neutron star mergers. So I'm going to begin with just 2 points on this plot here, and how much that has taught us just by the study of one neutron star merger and its electromagnetic counterpart. So the study of infrared fireworks is multifaceted, right? I mean, there are many different aspects of stellar physics involved. So we'll begin with the nuclear physics. And what is it about nuclear physics that forces us into this wave band, this piece of the electromagnetic spectrum, and to study it better? Okay, so we'll start with nuclear physics and heavy element opacity. So I hope all of you here have heard about what happened on August 17th, 2017. On August 17th, 2017, for the very first time, the LIGO and Virgo gravitational wave interferometers detected gravitational waves from the merger of two neutron stars. And this merger of two neutron stars sent off a ripple in the fabric of space-time that lasted for over 100 seconds. So this was much longer than what the Nobel Prize was given for, which was the merger of black holes, which was also from my colleagues at Caltech, so I'm not making fun of them. But it's just that black holes are very black, right? So as much as I love them, I congratulated them, as amazing as that discovery is, black holes merging are just not as fun for me as neutron stars merging. Because when neutron stars merge, there's light. And in fact, this example on August 17, 2017 was a mind-blowing, majestic event. Studying this event as it unfolded was like living a legend. It really was like you're in the middle of a fairy tale. I mean, I dreamt about this for a while, but I hadn't quite believed it would be so beautiful when it actually happens. Because when the merger happened of the two gravitational waves, 2 seconds later, there was a burst of gamma rays, and the gamma rays lit up. Few hours later, there was an ultraviolet, optical, and infrared counterpart. 9 days later, there was a radio and an X-ray counterpart. The entire spectrum lit up. There was nobody left disappointed. There were 70 telescopes on the ground and 7 telescopes in space that studied this event. Because when this neutron star merger happened, and all these free neutrons were ripped out of the system, they created heavy elements. And a black hole was born, and a cocoon broke out. So let me explain what this simulation here is, and you can ask me questions, and I have some more slides to go into some jet physics details if you're interested. But as you see these two neutron stars merging, they're ripping out material tidally, so there's just tidal forces that are ripping out the material, so there's a lot of free neutrons lying around. So when the black hole is born and a jet gets launched, this jet, instead of getting launched in vacuum in a completely clean environment, is getting launched into a big mess. Quite literally, right? I mean, there's few tenths of solar mass of material just lying around. So this poor jet actually gets stuck and starts to transfer its energy to the surroundings. So left is energetics and right is kinematics in this simulation. So the transfer of energy from the jet to the surrounding material helps form a cocoon. So cocoon is just the material enveloping the jet that soaks up the energy from the jet. And instead of being ultra-relativistic with a Lorentz factor of 100, it is mildly relativistic with a Lorentz factor of somewhere between a few to 10. So when I say mildly relativistic, the mild is a relative term, right? Because mildly relativistic is between 0.9 and 0.99 C. So it's quite large. It's almost the speed of light, right? But not 0.999999 C, which is what ultra-relativistic would be. So this very wide-angle cocoon, when it breaks out from the shell, is what gives you the gamma rays. When that cocoon goes and interacts with the interstellar medium, that's what gives you the X-rays and radio. The same cocoon is transferring energy into all of the neutrons, the free neutrons that are busy building up into heavier and heavier elements. And that's what gives you the nuclear synthesis. So let me now focus on this part of the slide. And this is just the periodic table. I'm sure all of you have seen this, learned in high school chemistry about different facts, why it's organized like this, what are the rows, what are the columns. By the way, it's 150 years now since Mendeleev actually came up with this periodic table and this very nice organization of elements in it. And if you look at this periodic table, most of the universe is actually quite boring. It's just hydrogen and helium. Supernovae that we now have tens of thousands of examples for. These are these explosions that are 1 billion times the brightness of the sun, are responsible for all the blue and light blue, depending on if you're a type 1 or a type 2 supernova. That's how all these elements shown in blue are made. So none of these elements are made on mines on Earth, okay? Mines on Earth are just like your retail store. They're not the fields where the grain is grown, okay? This is just where you go and pick them up, just like you go to a retail store and buy something. The fields where things are grown, these are the cosmic mines, right? So the supernovae produce all these elements shown in blue here. And the embarrassing fact is that before August 17, 2017, which is just 2 years ago, we did not know where half the elements in the periodic table heavier than iron were formed. Everything that you see in yellow here is now attributed just from this one event that we've seen in August 17, 2017 to the merger of neutron stars. Because these elements are formed by something called R process nucleosynthesis. So R process stands for rapid capture of free neutrons, right? So if you want to make heavier and heavier elements, what do you need in the nucleus? You need lots of neutrons. You also need conditions to be extreme enough in terms of density, temperature, the environment, that you can actually continue to build these elements and before they decay away, right? There's a race against the decay of the thing that you're forming and synthesizing heavier and heavier elements. So these conditions were ripe actually in the merger of neutron stars. And what we saw by combining data from 77 telescopes worldwide, and this is one example, you can read a bazillion papers with different data sets all coming to the same conclusion, is that when these two neutron stars merged, in a few hours the ultraviolet light was gone. The optical light lasted for a few days, and the infrared light lasted for a few weeks. So why is that important? Why is there being a red transient after a neutron star important? So let's go back to the periodic table here, right? So you must have learned in your chemistry classes that you start to fill the S shell, then the P shell, then the D shell, then the F shell. Does that ring a bell? Okay, I see a few nodding heads. That's good. So as you fill more and more shells, then just based on basic chemistry, you have more and more transitions, right? Because you have the quantum number factorial in the numerator for the number of transitions that an electron can make, the number of levels that an electron can jump around. So now when we're talking about things like lanthanides, right, which fit right here in the periodic table, you're talking about filling up the F shell, right? So G is 14, so 14 factorial on the numerator. So suddenly you're talking about, if you combine all these different elements, you're talking about millions of line transitions. So now when you have these heavy elements synthesized, some of them radioactively decaying, and the photon trying to escape from there and coming and trying to be detected by your telescope here on Earth, there's a big problem, right? Because there's so many possible line transitions that this photon has to go past a whole bunch of bound opacity, a whole bunch of possible transitions before it can actually make its way out. So the emergent spectrum, the light that comes out of such a system, is pushed out of the optical bands into the infrared bands. So the peak of the emission is in the infrared. So for a short period, because of all the jet and all the high velocity and the Doppler boosting, you could get a little bit of blue emission. But the hallmark signature is the red, the infrared emission. And the fact that this event here became red so quickly and so red that it was redder than any other transient that we had ever seen before, even though we've now studied thousands of transients of different flavors and sorts, was the smoking and the most important clue as to what was actually formed in these elements. And so all these different groups, right, they all converged on one thing, which is that heavy elements were in fact synthesized in this particular event. So now what you see here is spectroscopic evolution. So spectroscopy means you take the light from the source, you put it through a prism or a grism or a grating, any dispersive element, and you split the light into its rainbow, right? And that rainbow has the key chemical thumbprint of the transient. So you have something really, really hot, really, really blue, mostly featureless at early time. And as time ticks, you start to see all these bumps and wiggles in the spectrum. And these bumps and wiggles are different absorption lines, emission lines. Actually, there's no emission in this particular spectra. So different absorption lines of different elements that were synthesized in this explosion. So if you had a normal supernova, if you had a normal type 1a supernova, which is the explosion of a white dwarf, then at 6100 angstrom, you should see a deep silicon 2 absorption. If you had the death of a massive star, you should see hydrogen and helium lines. But in this particular case, you see this complex blend of lines of many, it's not just one element, right? There's a huge debate on which element and how many elements and how much of which element was synthesized. But you see this characteristic signature of something which has lots of line transitions, lots of elements, very high velocities, all being blended together and forming these features. Ajit. That's the million-dollar question right now. So there's some claims that some of these lines are due to neodymium, some claims that cesium and tellurium, but much debated, right? Some claims that there are these 5 elements. This is a Japanese group. Everybody is trying to understand what these elements are. But
because we don't know the terminal velocity.
The velocities are really high. The velocities are between 0.1 and 0.3 C. So all the line transitions get blended.
So what is the trouble with understanding which elements are they?
There are only 13, so there are the total number of elements that are synthesized by the R process is everything from atomic number about 80 to about 200, right? And out of these elements, only 13 elements have all the line transitions and Einstein coefficients mapped.
Really?
Yeah, so Dan Kaysen's model, which is the leading model in this study right now, is based on 13 out of the 120 elements.
There are no lab experiments.
Some of them are done, but some of them are classified because you have things like uranium. so some national labs have more data that people are trying to get at, but it's classified. So that you run into like these practical issues here. So there's a lot of debate actually on what lines actually, which elements actually contribute here.
Why was it broad? I mean, they were fairly broad at that.
Absolutely, yeah.
No, and the gaps, the absorption gaps, the finely when the things settle down, big windows.
Okay,
There's no light in the back.
Oh, so sorry. So when you look in the infrared, there are these bands which are due to telluric absorptions from the Earth's atmosphere. There are gaps in understanding because the Earth's atmosphere just removes these gaps, right? Yeah. No. This is just very boring, actually. This is just the atmosphere of the Earth, which is removing that piece of the spectrum because it's completely telluric absorbed. So there's OH lines in the Earth's atmosphere which are stealing away this piece of the spectrum. If we could get a spectrum with Spritzer. Spritzer was still cold, and unfortunately it's run out of cryogen. So I would love to go to space and get a spectrum of this. With JWST, it would be possible. Okay, but that's exactly where I was going with these questions, right? Which is, what did we see? Okay, so I think everybody, the entire astronomical community, the entire nuclear physics community agrees that heavy elements were synthesized. Now, which of these heavy elements was synthesized is the question, right? And was the production rate high enough? So let's first take the whole and then we'll break it up into parts. So something like 10,000 Earth masses or 0.05 solar masses of material was synthesized in this event of heavy elements. Let's just put them all in one big category. We're not discriminating right now. So if you take the total based on the light curves, the spectra, the modeling, something like 0.05 solar masses of material was synthesized. If you take some median rate, right, I mean, LIGO has a lower limit. Based on my PhD thesis search, there's an upper limit which is stricter than the LIGO upper limits. That's why I like this one better. And then you take a number in the middle, which is 500 events per gigaparsec cube per year. You take the number of times you see neutron star mergers, and you multiply it by how much material is synthesized by any one event, then the total is roughly the solar abundance. So they're pretty good sites to produce heavy elements. They could explain, in fact, some people say they over-explain the observed solar abundance. So as a whole, it really works as a site. But now the details are a little bit more problematic, right? How do we, if you look at the solar neighborhood, this is now the abundance as a function of atomic mass number. So these heavy elements are sort of in these 3 peaks that you see here, the first peak, the second peak, the third peak, and the lanthanide. So you don't have all elements in equal amounts, right? You have this distribution as observed in the solar neighborhood. And if you make a cumulative version of the same plot, right? This is the same data just shown twice. then about 75 or almost 80% of the elements are actually very light in the solar neighborhood. They're the first peak. So they're the first row that was shown in yellow in the periodic table. So now the question you may ask is that how good is this neutron star merger at forming the heaviest of the heavy elements? So some of you may remember that there was a lot of press coverage when this event went off about that we found out where gold and platinum is synthesized. Does anybody know what the atomic mass number of gold and platinum is?
Maybe 80 or...
Right. So they are somewhere here. Au is here, platinum is here, right? So they're actually the heaviest of the heavy elements, right? Because all these guys fit here, right? So this is actually in the third peak of this plot, right? And the third peak, it's very rare. Out of the 10,000 Earth masses, if you divide them the way you see them in the solar neighborhood, only about 10 Earth masses is in gold and platinum. Yet all the media was like, okay, we have struck gold, we found gold and platinum, because that's what appeals to the general masses, right? I don't know, silver is a better bet because at least silver is lighter and it's in the first peak, so I would have felt a little bit more comfortable if it was striking silver than gold. Because if you look at the data that was in hand, if you take the data from these 70 telescopes around the world and 7 telescopes in space, and you try and model it, and you say, if I make a model with gold and platinum, and make a model without gold and platinum, which one is a better fit to the data? And statistically, there's no difference. They're both consistent, okay? So the ground-based data is not conclusive on whether or not all 3 peaks were synthesized. Now, some of you may be married in the room, and some of you may wear golden wedding rings or golden wedding necklaces or whatever it is when you get married. So gold is important to you personally, right? So you still want to find out the answer to this question of whether or not the heaviest elements were synthesized. So how do you do this? If the data from 77 telescopes around the world, which is the most majestic observing campaign, is not able to answer this for you. So then you go back to basic physics. Right, you open up your textbook and you start looking up half-lives, radioactive half-lives of various elements. And you ask the question of what is the fraction of electron heating, right? So if you have all these 120 elements, they have different half-lives, you know how much electron heating each of them contributes, and you plot them up by splitting them into first peak, splitting them by atomic mass ranges, right? So you split them up into first peak, second peak, third peak, lanthanide, and you just make this simple plot based on basic physics, right? There's no detailed, complicated modeling in here. And what you would notice is that...
What do you mean by fraction of electrons?
So if you have radioactive decay of the element, then how many ergs per gram would you get per second per gram would you get from a particular element? And then you sum them up, that's it, right? So this, and you normalize it, so that's why it's a fraction. So for the lightest elements, you actually get this green line, which means that the first peak, the silver and the thing that is 80% of the solar neighborhood, the lighted elements, they dominate in the first about 20, 30 days, right? And then they start to drop off after that. The heavier elements actually dominate at late time, right? Because they have slightly longer half-lives. So the math works out, or the physics works out to say that the lighter elements will dominate at early time, and that's why this data is no good because it ends at about 3 weeks, right? There's nothing more than 1 month on this plot. And actually there was a problem. The reason there was no data after this was that the neutron star merger went too close to the sun. And this is exactly what happened to me this morning. Like I might have just canceled this colloquium because at 10 o'clock, as soon as Ajit walked into my office, my phone rang because there was a binary neutron star today, this morning, detected by LIGO and Virgo. And it's a real event. It's a binary neutron star merger at 200 megaparsec. And I was willing to change tracks completely and trigger all the telescopes in the growth network. And there's a lot of work to do when a trigger like this happens. Except that about 15 minutes later, I realized that this event is too close to the sun. So none of my telescopes can actually look that close to the sun. So sadly, even though it's a real event, and it's happening right now, and it's just emitting all its photons so close to the sun that none of the telescopes can see it. In this event, it was also very close to the sun, but you could observe it for a month before it was completely lost, and the sun played spoil support here. So anyway, back to this event. So now we need something that can fight against the sun, right? How do you fight against the sun and look close to the sun? There's only one telescope that can do this, and this is the same Spitzer Space Telescope, which my first PhD student's thesis topic was on. This is one of NASA's 4 great observatories, and it's in this amazing L2 orbit around the sun. So it can either look very close to the sun or very far from the sun. And it so turned out that its visibility of this event opened up at 43 days to 74 days after merger. So this event, while everybody else gave up, this one infrared telescope, the Spitzer Space Telescope, was able to observe this event at 43 days and 74 days. So look, that is about here and here on this plot. Very, very critical points on this plot. And as you can see from this diagram, this is the host galaxy, NGC 4993. You see this red dot here? That is the neutron star merger. If you do a bit subtraction, you see it as this white dot here, and it fades away in this plot. This is barely 4 sigma, so I don't know how many of you will believe it, but trust me, we've done many tests to ensure the statistical robustness of that detection. So there are 43 days and 74 days, and detections at 4.5 micron, right? So this is beyond the optical in the reddest bands. So what does this mean? So if there were only light elements, if there was only silver in this event, no gold in this event, then we would not expect to detect anything at 43 days and 74 days. It's all long gone, right? This green line has died by the time you get to this phase. The fact that you detect anything at all, you can model it and try and figure out what is it that could produce elements at this phase. So, and it turns out, actually there's only 8 elements in the periodic table that have the right half-life. And these are all elements in the 2nd and 3rd peak. So there's barium, radium, neodymium. Remember the neodymium from the spectrum? Thorium, europium, osmium. You can see these 8 elements. These are the heaviest elements that we could see, right? And as Professor here just pointed out, if you could get a spectrum at this phase, right? If something like the James Webb Space Telescope was launched at the time of this event and could get a spectrum of this event, then we predict in our paper that you could actually see line transitions from these events. Because now you're not dealing with a zoo of 120 elements, right? You're actually dealing with very specific elements with very specific line transitions, and that you should be able to see in the mid-infrared bands and not be contaminated or confused by anything else. And also at this late phase, things slow down, right? In the early phase, the cocoon and the jet and all this relativistic stuff is transferring so much energy into the system that things are moving very fast. And when things move fast, lines get broadened and blended. At 43 days and 74 days, you're more optically thin. That's the terminology you use, which is that things are moving slowly. So the line transitions should be more isolatable and identifiable. So the next time we see a binary neutron star merger, we should look for these elements in the spectrum. Do you have a question at the back there? Did you have a question? Okay. Feel free to ask any questions that you may have, okay? So I've spent quite a lot of time talking about one event on August 17, 2017. It was just life-changing. But let me now bring us to 2019. 2 years is an eternity, right? Things should have happened. So after August 2017, for about a year and a half, the gravitational wave interferometers were turned off. They were doing engineering. They were trying to make them more sensitive and make them upgrade them. So they only turned back on April 1st of 2019. And as of this morning, there are only 9 rows on this table. I forgot to update the slide, but as of this morning, there's a 10th row on the table, which has been deemed to be real. And there are 10 triggers which have at least one neutron star in the system. So it's either binary neutron star or a neutron star black hole. So,
So the 10th one which you said is too close to the sun right now?
Yes.
But like after a few days, would it have transited?
Yes, but unfortunately, I think the emission would have faded away. So I think we lose it completely. That's the sad part, right? I mean, no, radio can still do it, right? So radio is the only thing that only game in town when the sun is close. The optical and the infrared and the UV are a struggle.
Before they have trouble localizing.
Yes, yes. So the radio now, the problem is how do you map large areas? And there are things like ASKAP, for instance, that now have large fields of view. And I'll show you an example of ASKAP mapping 23 square degrees. This thing is about 2000 square degrees, so it's a bit difficult. I think if it was less than 100 square degrees, then radio is capable of mapping that area to limits that are interesting. So there was one event here, which was 23 square degree localization. And there I think radio did a very good job, especially this ASKAP telescope in Australia. So my newest collaborator is actually from University of Sydney, Tara Murphy. So I'll show you a little bit more about that. So hold that thought. But this here's a summary of the events, right? And you look at this and you say, okay, let's look at the false alarm rate for instance. This is, how significant is the event in the gravitational wave data? Most of these events are one per year, one per few years. There's only two events, this neutron star black hole, and one per 10 to the 25 years, and this one here, this binary neutron star at one per 69,000 years, which is very high significance. The others are marginal, but that's how life is, right? I mean, most things happen right at the margin of your detection threshold. In terms of the localization, the median localization is 1200 square degrees. It's very, very large. Hopefully when LIGO India will get built really, really quickly, because once there's LIGO India, then the degeneracies and localization can be broken. And having that LIGO India interferometer will make this whole challenge, I mean, you'll cut this by at least 2 orders of magnitude. To a few hundred square degrees, not these tens of thousands of square degrees. This is crazy localizations. The entire sky, the night sky is 42,000 square degrees. So if you tell an astronomer this happened in 24,000 square degrees, that's half the sky. That's not fair. That is very difficult to find the counterpart in that much sky, right? Because the universe is so dynamic, so many things are spatially and temporally coincident. How do you know which one is actually related to the neutron star merger? Okay. So right. So this is basically the significance of the detection, the signal to noise of the detection in the gravitational wave data. So if the event was too far or it was at a non-optimal angle, then you don't get as much signal to noise in them, right? So Anajit can answer this with more detail. Yeah, it's just the significance of the event. How real is it? Right? How much telescope time should we spend on this? Okay, and the distances are quite large. There's even one at 600 megaparsec, which is quite far when looking for these counterparts. Nevertheless, that hasn't stopped us. We have even dared to search a pie of the sky to look for the counterpart. So as I said, in the optical wavebands, we have these wide field cameras. We have this Wiki transient facility at Palomar Observatory, which can image 3,000 square degrees an hour. So even though it's crazy to think that you're searching a pi or 2 pi of the sky for the counterpart, we've done it. So we've imaged these large areas and looked for counterparts within minutes of this thing actually happening. In fact, this is a distribution of our response time. So from the phone ringing to pressing go and on the telescope and the telescope actually observing, we've had minutes. In fact, in one case, the trigger happened about came out half an hour after the merger. And because the sky localization was so big, we were anyway surveying that part of the sky. So even before we knew there was a neutron star merger, there we had serendipitous data for that part of the sky. So we have very, very good early time data in response to these events that have happened. But the sad truth is that 10 triggers later, in the last 6 months, we have not found an electromagnetic counterpart. So what does this mean, right? I mean, we definitely have the sensitivity, we definitely have the response time, and if you do basic statistics and you take 1 minus P1 multiplied by 1 minus P2, etc., and you compute what is the probability that we should have seen the counterpart, it is well over 99%, right? So what this means is that the luminosity function of these events is that they're not all as bright as GW170817. That really was a gift of nature. But if you look at the full sample and assume all of these events are real, then our non-detections are telling us that these events are either too faint, so they're fainter than about minus 16.5 absolute magnitude, or they're too red, and we don't have the red sensitivity.
So you factored the distance already?
Yes. So we have luminosity function constraints which say that it has to be either fainter than minus 16.5 or redder than 1 micron. So, because there are too many of these events, right? I mean, the assumption is that they're all real. Now, if later post-analysis of the gravitational wave data says, half of these are just garbage, then our limits don't mean anything. But if you assume that they're all real and they all have a counterpart, right? And you ask a model-independent question. I'm making no assumptions on the model. I'm just saying that I've looked at each one, and I've gone so deep, and here are the distances. They translate to these upper limits, and I combine the limits based on the 1 minus p's of each one. Then I can get a model-independent luminosity function. And that model-independent luminosity function suggests that these are either much fainter or much redder than GW170817. So let's look at one event more closely before we try to solve this puzzle about the faint and red. Sure.
In the previous slide with the, so you had this high significance neutron star binary, the fourth line. That's probably a real event.
Yes.
And very localized also.
Yes.
But the signatures there are probably different from the August 2017 because that was binary neutrons. So is it very different or qualitatively?
Fantastic question. Those are my next 3 slides. So as the question just pointed out, on August 14, 2019, there's again a remarkable moment, right? We know that we had, at least with binary neutron stars, we had known from studies of pulsars, the Hals-Taylor binary in particular, about a dozen or so binaries in our own galaxy, that 2 neutron stars can orbit each other, right? We've seen them as pulsars, even before LIGO was built and detected anything. So that was fantastic, but at least that was expected. Now, in our own galaxy and through other astronomical means, we have never seen a neutron star black hole binary. And now, on August 14th, 2019, just a few months ago, LIGO Virgo claimed that at a rate, with a significance better than 1 per Hubble time, right? That's crazy signal to noise. With a localization of 23 square degrees, they believe they have found a neutron star black hole binary. Okay, this means no sleep for 1 month straight, because you have to look with every telescope possible to try and find the answer to this question of when a neutron star merges with a black hole, what happens, right? There are some theories, there are some ideas, but I'm an observer. For me, seeing is believing. So for me, when this event happened, we wanted to search it with anything and everything we could throw at it, right? So the first paper that we published was a radio search by ASKAP. This is an Australian telescope which has a very wide field. So in one pointing of this telescope, we could actually search that entire localization of 23 square degrees. And there was one candidate that got us excited for some time, but we later convinced ourselves that this is actually just a supermassive black hole, just an AGN in another galaxy. I know some people really like supermassive black holes. There's a workshop here on that next week, Ajit told me. But for us, it was a big disappointment because it was not related to the neutron star black hole merger. But based on the non-detection, we were able to constrain the circumstellar environment density as well as the observing angle. Right? The reason I'm showing the radio plot first here, so this is a paper led by a young graduate student, Dougal Dobie, of my co-I in Australia, Tara Murphy, was that neutron star black hole binaries, we've never seen them. We don't know where they happen. But they're so difficult to form in a compact configuration, such that they merge in less than a Hubble time, that some people believe, and this is debated, that instead of just forming them through the standard channel where you start off with 2 massive stars, they go through their whole life, and one explodes a supernova that forms a neutron star, another explodes as a supernova that forms a black hole. People think that's a very difficult channel to keep that binary together at the end of its life. So instead, people have proposed that to form this neutron star black hole binary, you need a third object in the system that keeps these 2 bound. And that third object in the system, through Kozai-Lidov mechanism, is proposed to be a supermassive black hole. So in the centers of galaxies, you're expected to find these neutron star black hole mergers. So if they happen in the centers of galaxies, now that could be messy because the black hole in the center of the galaxy does many things, but that could be really a boon for the radio. Because when you're looking for radio emission, you're looking for interaction with the interstellar medium. And the interstellar medium density is much higher closer to the nucleus of the galaxy. There's just a lot more stars there than anywhere else in the galaxy, right? So, but in this particular case, a non-detection in the radio, the fact that none of the radio candidates panned out, allow us to rule out circumstellar densities down to 10 to the minus 3 depending on what the viewing angle is, and up to 10 for the larger viewing angles. So this is a very significant upper limit here. In the optical, I almost lost a few heartbeats because of this event here. We did a deep search with the dark energy camera in Chile. So in Chile, there's a beautiful 4-meter telescope, which is called the Cerro Tololo telescope, and it has a 3 square degree dark energy camera. And when we saw this event, we just couldn't believe it, right? Because this event happened in this beautiful blue star-forming galaxy. It happened at the right place. It was smack in the center of the localization. It happened at the right time. There was no history of variability at that position from any other survey. It happened at the right distance. The distance to this galaxy was exactly consistent with the distance expected from the gravitational waves. If you take the distance and the brightness, the absolute magnitude was minus 15.6. So it means that it has the right luminosity as well. And the best part was that if you look at the I band and the Z band data, it was reddening. And this reddening is a really big clue. It's a hallmark signature for detecting these events. Now the amplitude is not very large of the reddening, but this reddening, this color evolution was a very, very important clue. So we thought we had it. We really, really thought we had it. So we triggered our best telescope, the biggest optical infrared telescope that we have, which is the Keck telescope in Hawaii, to try and get a spectrum of this event. And it was very difficult. It was very faint, but we did manage to get a spectrum. But sadly, that spectrum that's shown here shows this broad feature at 10,830 angstrom, which we have seen before in supernovae. So it is a helium line instead of, which is way up in the periodic table, and none of these heavy elements. So our conclusion was that this is just a heartbreak moment. It's not the electromagnetic counterpart to the neutron star black hole merger. But we looked at every single candidate through a lot of hard work in many telescopes, but did not find the counterpart. So what does this upper limit mean? You have a high significance event. It's very well localized. You've really imaged every piece of the localization. You left no chip gaps, nothing, right? This is the intensity with which we imaged it, not once, but 7 times to try and look for the counterpart. You can convert it to, again, constraints on opacity, on viewing angle, and ejector mass. And so this is the allowed region, and this is a region of parameter space that we can rule out. And you can see that GW170817 would get ruled out by this exercise, right? So it means that neutron star black hole mergers could be very different from neutron star mergers. It's very possible in this particular scenario that what happened here is that either the black hole was not spinning fast enough, or the tidal deformability parameter was not the same as in the equation of state is maybe not the same for the neutron star companion in this particular case. And maybe the neutron star was just swallowed whole by the black hole. That's entirely possible, right? If the mass ratio especially is too extreme, say the black hole was like 10 times or 20 times more massive than the neutron star, then there is a possibility that you're just left with no material to light up the photons. All of it just falls into the black hole and is swallowed in one big fell swoop.
That's something the gravitational wave signal should do.
Yes, if they publish their paper. Mass ratio, yes. Mass ratio, inclination angle.
Yes, yeah.
I've been nudging my physics friends, please write your paper. We finished writing our papers, they're published. So I'm hoping soon. I think it is on their high-speed writing list, right, is what I understand. So any day now, we should see what the real answer is here. But even without that precious information, we can constrain Q, which is the mass ratio, lambda, and chi. All of these should have some constraints from the gravitational wave data. So they can tell us if we were right or not. Now, this shouldn't happen all the time, right? So there's some, again, parameter space in this particular binary system where the mass ratios should allow an electromagnetic counterpart. But would it be red or blue? My worry is that it's not just faintness. It's faintness in the optical bands. It could actually be really bright in the infrared bands, right? Because of all this bound opacity, the emission is coming out of the optical and moving into the infrared. So what I'm showing here is a theory paper by Dan Kaysen and collaborators, where he shows that depending on the parameters of the system, like the mass ratio, the viewing angle, the remnant lifetime, how quickly do you collapse to form a black hole? This year is by 2 neutron stars. This year is again 2 neutron stars but different viewing angle, different mass ratio, shorter lifetime. This year is a neutron star black hole system. The red component, right, this torus here, survives in these cases. The blue component is actually easy to suppress. So maybe this is what is at the heart of the problem here, that we've had 10 events but no electromagnetic counterparts, is that there are many ways to suppress their optical emission, and the GW170817 was just a gift of nature that happened to be, the viewing angle was correct, and the remnant lifetime and the mass ratios was almost 1 point something. It was actually really good, and we saw the blue component. In these other situations, we may not be as, that may not be the norm in the distribution here. And so this increases and emphasizes the urgency of trying to build a wide field infrared system, right? So 23 square degrees was the best localization we had. And the other localizations were 24,000 square degrees. And if I only have a 0.6 square degree camera, I'm out of luck, right? There's no way I can go and image such large areas with such a small camera. So how do you build a bigger camera? And that is this project. This is the phase 4 in that infrared roadmap that I showed you, where with my collaborator, Professor Rob Simcoe at MIT, we are exploring alternative semiconductor technology to try and build infrared detectors. So instead of using the tradition in astronomy has been to use mercury cadmium telluride, which are semiconductors that you use in your detectors inside your cameras. Instead, we're using indium gallium arsenide. So indium gallium arsenide actually has been used in the commercial world to make these night vision cameras. It's used in defense. It's just not used in astronomy because these cameras are much more noisy per pixel than these more expensive mercury cadmium telluride detectors. But these things, we can modify the electronics and make them suitable for our purposes. And they're a factor of 5 cheaper per pixel. And for me, the key metric is how many pixels can I put in the focal plane? How big a field can I get so that when LIGO Virgo tell me that a gravitational wave event has happened somewhere here in the night sky, I have the ability to go and map it. The same way as I do in the optical right now, I want to be able to map it in the infrared. So just yesterday, so a year ago, we got funding for the Winter project, which is a 1 square degree on a 1 meter telescope. So it will have sensitivity to a neutron star merger at 200 megaparsec, and this will be at California in 1 year from now. And just yesterday, we got funding for the DREAMS project, which is the southern counterpart of this in Australia. And it was just yesterday, literally, I got the email that the Australian Research Council has given us funding to build the southern counterpart of this object. But now we can focus on where the spectrum peaks and not hope and beg for some photons in the blue end, right? If the spectrum peaks in the infrared, you should search for it in the infrared, right? That's the basic idea here. And our hope is that once these two, this northern and the southern telescopes are ready, then we can go to Dome C, which is in Antarctica. Because as I mentioned in the beginning of the talk, it's 40 times darker than anywhere else on Earth. And the seeing, if you are able to get yourself 20 meters above the ground, and we have an idea of how to do this based on the facilities building there at this French-Italian base, but I need to make friends with more French and Italian people to make this a reality. So this thing is not funded. This is just a dream right now. So let me just add that caveat. We've just come up with a funny acronym to entertain ourselves right now. It's not a real project till it gets funding. But I would really like to go to the South Pole because it's much more affordable than space. And you can get to 23rd mag depth at 100 square degrees power by 2025. So for LIGO Virgo's A+ sensitivity, this would be the game in town that can look for neutron star black hole mergers at 400 megaparsec. Ajit, how much time do I have left? Is that clock correct? 5 more minutes? Okay. So let me, I'm going to skip most of the rest of the talk because this was the most important part on nucleosynthesis that I wanted to convey. But just as a teaser in the last few minutes I have here, let me tell you about this, my second student's thesis project. This is an Indian student, Kishale De. He's from Bengal. He did his undergraduate work at IISc. And he's now doing a PhD with me. And in preparation for opening up this wide field infrared that I just motivated for you scientifically right now, what he built was a telescope called Palomar Gattini-IR. So before we have detectors, before we have these alternative semiconductors, before we have cameras with which we can fill the focal plane, we can do another thing, right? Which is we can take a small telescope, a 30 centimeter telescope with a very fast beam. The entire telescope is just this piece here. This is just the baffle. The whole telescope is just this big. But at the back of it with a fast beam, you can put one detector that has very coarse pixels, right? So you can give up spatial resolution to get more field of view. Right? So you have much poorer spatial resolution. Each pixel looks at 8 arcseconds instead of 1 arcsecond, and you can get 64 times the field of view, right? So this is a camera with a field of view of 25 square degrees. So 25 square degrees, I just told you the moon is half a degree on the sky, right? So 25 is 5 by 5. So it's about 100 full moons on the sky in one shot. And as you can see in this movie, this telescope is able to image huge swaths of the night sky, something like 15,000 square degrees down to J of 16th mag every 2 nights. And this is entirely driven by one graduate student and one postdoc, Matt Hankins. And we actually began survey operations just a few months ago on July 2nd. And the goal here is that now this is a small telescope, so we can't go very deep. So we can't do the neutron star or the neutron star black hole merger question. We need a much bigger light bucket to be able to achieve that. But what we can do instead is another facet of multi-messenger, which is a supernova in the Milky Way. Now, one of the things that I at least, I don't know how many other astronomers feel this way, is that if there is a supernova in the Milky Way, the neutrino detectors would go crazy. There'll be so many beautiful detections. But the optical detectors may be out of luck because it's more likely to happen when the stars are, and the stars are in the middle of the galaxy. And in the middle of the galaxy, there's so much dust along the line of sight that we may just not be able to detect anything due to line of sight extinction. Now in the infrared, the wavelength is longer, so the photons can go around the dust, and so you can detect events out to very deep column densities in the Milky Way. So no matter where in the galaxy the supernova happens, this little telescope should be able to detect it. Now, I can't ask my brilliant graduate student to wait. The rate of supernovae in our own galaxy is 1 per century. It would be very sad if he's writing a PhD for 100 years, waiting for the supernova to happen. I think that would be quite mean as an advisor. So instead, what he's doing, I'm going to skip some of these slides here, is looking at novae in our own galaxy, which are more guaranteed. And while he's waiting for the supernova, he started looking at this problem with classical novae. So let me explain what a classical nova is. So classical nova is a white dwarf with a companion. Mass transfer onto the white dwarf is causing some fireworks on the surface of the white dwarf. It's not a billion solar luminosities, it's only about 1 million solar luminosities, and it repeats once per year, once per 10 years, or once per 10,000 years, depending on the details of the system. But what is cool about these novae is that some of them have gamma rays. So there's shock, and in the wake of the shock, there's dust. So these could be very, very dusty events. And so theoretically, it's been predicted that there are 50 novae, 50 novae per year in just our Milky Way. Except if you look up how many we've actually found, again, as a full global community, it's 5 novae. So where are the other 45? And one problem is that they could just be hidden due to dust. So with this infrared telescope that's mapping the entire northern sky every 2 nights, Kishale started to find these very, very reddened novae. So it's something that is so bright, you can just see it, right? This really bright light is the new star in the infrared bands. In the optical, you don't even detect it because there's 14 magnitudes of line of sight extinction, because it's just 0.2 degrees from the plane. So he started building this inventory of novae in our own galaxy while he waits for the supernova. And this is giving us a lot of tools, a lot of technical tools to be prepared for these more ambitious infrared surveys that we're trying to build over the next few years. So it's 12:30, so I'm going to just skip right ahead to my last slide here. And I hope I've convinced you that the dynamic infrared sky is ripe for exploration, And I'd like to thank you very much for your time and attention and take any other questions.